One of the challenges of integration by substitution is choosing the correct part of the integrand to be your u. So here's some pro tips, some guidelines to help you along the way. So try letting u equal some complicated part of the integrand. The complicated part is your u because you also have to have the derivative of that complicated part as part of the integrand because it came from the chain rule. So think about derivatives here. If I let u equal, let's say, x squared, then taking its derivative gives me 2x, and 2x is simpler than the x squared that we started with. Now, the obvious choice here is you have yourself a composite function. Your u should be the interior of that composite function. But sometimes it's not quite as clear as that. So here's another thing. So some function whose derivative is also part of the integrand, right? Because again, it came from the chain rule. Sometimes though, what we find is missing is some sort of constant, right? So what I'll have to do is I'll have to multiply by a fancy 1 and then basically use the constant multiple rule, which for integrals allows us to take a constant out, right? Because it was based on some summation rule. And please understand that you may not choose the correct thing the first time. So what do? You don't quit, you go back and you try something different, some other thing to be your u and see if it works. At the very, very end, of course, you could just take the derivative of your answer and see if it matches up with your integrand. So let's take a look at another one of these. We're going to start from scratch here. So on example 2, find the antiderivative of 2x times x squared plus 1 squared dx, or with respect to x. So first of all, how do I know that I'm going to use integration by substitution? Well, I have a product of two functions. And there's no product rule here for our integrals. There's a product rule for derivatives, but not for integrals. Okay. And then the other thing is that not only do I have a product, but I have a composite function. I have x squared plus 1 inside of a squaring function. Now, one of the things that you could do, like you could avoid doing integration by substitution if you expanded all this out and then distributed your 2x through that, but nobody wants to do that. Instead, we're going to do u substitution. Is it obvious to you what your u should be? Again, I'm going to choose the more complicated part of this. I'm also going to choose the part as the interior of a composite function. And not only that, if you think of its derivative, isn't its derivative just also part of the integrand? It actually fits all of those little pro tips. So I'm going to let u equal x squared plus 1. And then I also, since it's a chain rule, I also have to have its derivative as part of my answer. So I'm going to take its derivative. And instead of going du dx, I'm going to go du is equal to, take the derivative of the right-hand side, 2x, and then a dx on the other side, right? Because it just came from the other side, I'm going to kind of speed up the process here. So I can see that from my original integrand, I have my x squared plus 1 right here, and then the 2x dx, the 2x and the dx are right there. Everything is accounted for, so I'm going to rewrite my integral like this. My integral, my antiderivative of the 2x together with the dx is going to become my du. So I'll write that part down, du. That's an x, du. There we go. And then the x squared plus 1 squared is going to become our u squared. U squared. There it is. So it's as if I'm just taking the antiderivative of x squared, which we can do. That's easy. It is u to the third power divided by 3, and then plus c. Last thing to do is a back substitution. So we don't want our answer in terms of a u. We want it in terms of x. So I'll take this x squared plus 1 here, substitute it in here for this x. I'm going to write this as a 1/3 x squared plus 1 to the third power, and then plus c. And here's my answer. Boom, 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 boom. I'm going to suggest getting in the habit of just either mentally or on your paper taking the derivative of this and seeing if it matches up with what we started. So this 3 is going to leapfrog down. It's going to cancel out with this 1/3 when we take its derivative, and I'll just have x squared plus 1 to the second power. And then since you have a composite function, you'll have to multiply it times the derivative of the interior, which is just 2x. And the derivative of your c, of course, would just be 0. And that is the same thing as this, right? It's just it's multiplication, so the order of that thing. It doesn't matter. All right. So this was, it's a little bit contrived. And the reason why it's contrived is because our du was perfectly right inside of our integral. That doesn't always happen. So sometimes we have to fix it to some degree. So let's take a look at example 3 and see if you can notice the difference between these two things here. I think it's a little bit easier to see on the slideshow right here. So here's example 2 that we just did. Here's example 3. Do you see the difference? Right? The only thing that's different is that we're missing a 2. So how is that going to affect the substitution? Well, it still seems obvious that I'm going to use the x squared plus 1 as my u. Take its derivative, du is equal to 2x dx. But here is the issue. The issue is that I'm supposed to have a 2x, but I only have an x. Well, you know what I'm going to do? I'm going to go ahead and I'm going to force a 2 here. Okay, the problem is I just made this thing twice as big as it used to be. So I can compensate by also multiplying by half, and I'll multiply by half right out front. Because essentially what we just did, if I combine these two things, I get a 2 over a 2. We multiplied by a fancy 1 right there. So that's the technique. If you're missing a constant, we'll just go ahead and multiply by that constant and then fix it, compensate for that constant value that you just changed your integral by. So now let's go ahead and rewrite stuff. The 1/2 that's on the outside, it stays. 1/2 indefinite integral of the 2x with the dx, boop, becomes your du. Let's write that right there at the end. And then just like before, your x squared plus 1 squared becomes u squared. U squared. So the integration is almost exactly the same. We still just have this 1/2 that's going to go along for the ride, that constant multiple. And we'll do our u to the third power over 3, and then still plus the c. Actually, the c would also be multiplied by the 1/2, but it just makes it another constant, and we might as well just call that constant also c, whatever. All right, and then, simplifying here, I would have a u to the third over 6 plus c, and then we want to rewrite stuff back in terms of the original variable x, take out the u, substitute your x squared. Here, actually, let me make that as a 1/6 there. Make it look real pretty. 1/6 times x squared plus 1 to the third power plus c. Let's verify that. Let's go ahead and verify it. We'll take its derivative. All right, so leapfrog that 3 down, and when we do, we're going to get 3/6 times x squared plus 1, decrease the power, 2, multiply it by the derivative of the interior, it's 2x. So of course outside here, that fraction will reduce to a half. Where's the cancellation crayon? That's not correct, but I'll use it anyway, so that's 1/2. And then we, of course, can take 1/2 of the 2 that's part of the derivative of the interior function, and then rewrite everything as an x squared plus 1 quantity squared times just x, and if I'm not mistaken, that's exactly what we started with there. So again, sometimes what I'll have to do is I'll have to multiply by a fancy 1 to fix any kind of constant multiple. That's all you can fix. You can fix a constant, but you can't fix a function. Like if this was an x squared that's here, and I only had an x, I got to do something different. All right.